Okay, hello Poppets. All right, we're going to talk about neuronal transmission now. Neuronal transmission is transmission between two neurons. So what you see here, you've got here a presynaptic neuron. You've got a cleft or a space in between the two neurons because they don't physically touch each other. And you have a postsynaptic neuron here. So when you're talking about neuronal transmission, this is thought of as a chemical, electrical, chemical type of communication. So let me explain what it is that I'm talking about. So when you look at the presynaptic neuron, you can see it's got the dendrites that receive information, and they have their receptors on them that would connect with neurotransmitters like a lock and key. And together, that would be dumped in at the axon hillock. And if there was enough excitability generated there to reach an action potential, then what you're going to see is this electrical action potential being carried all along the length of the axon. So you've got an action potential arriving here. Now, this action potential triggers the release of calcium, and calcium basically is allowed to open in through a voltage gated channel, and it enters into the end terminal of that presynaptic neuron. Now notice these bubbles inside the end terminal. Most of the time those are just sitting there and the neuron will physically make that neurotransmitter. But when calcium comes in, some of these bubbles are actually quite close to or even attached to the membrane of the end terminal. And calcium triggers a process called exocytosis, which causes the membrane to fuse with the vesicle and allow that neurotransmitter to be released into the synaptic cleft. So this is a transduction of an electrical signal into a chemical one right here. Now, the neurotransmitter is going to diffuse across the cleft, and it's going to hook into the receptors on the dendrite of the postsynaptic neuron. And again, that follows the same lock and key idea that you've had from all of your other biology classes. That chemical signaling is going to be, again, computed at the axon hillock of the next neuron. And assuming that you had an excitatory saying, yes, go ahead, send the signal, then what it would do is be transduced back to an electrical signal here, and that would carry on down the axon of the next neuron across. So again, to recap, you've got an action potential being propagated down the axon of the presynaptic neuron. Action potential triggers an influx of calcium through a voltage-gated channel into the end terminal. The vesicles holding neurotransmitter start to exocytose, which means that they fuse and merge with the membrane of the axon end terminal. The neurotransmitter then diffuses into that space between the two neurons, the synaptic cleft, and will then start to attach to the receptors of the dendrite of the next neuron down, the postsynaptic neuron, causing another computation at the axon hillock. And if you've got an excitatory postsynaptic potential, enough of that, it'll propagate a new electrical signal down the length of the axon. And you might be wondering, well, what happens to all of this neurotransmitter there? Surely you don't want to leave it. And that's a great point. You don't. Because if that stayed just remaining there, what it could do is it could trigger a neuron over and over and over again. So there are different things that happen. Sometimes you'll get the neurotransmitter taken back inside. You get reuptake, and it goes back inside the axon end terminal so that you can use it again. Sometimes what happens is you actually get enzymes that would come in and they would break this down to get rid of it, kind of like taking out the garbage. But either way, they have to clear out the synaptic cleft so that you don't get unwanted electrical and chemical signaling going on. Okay, and that is the basis of neurotransmission.